Now in this video we will see some of the results on normal subgroups. The first result is if H is a subgroup of a group G with the index of H in G to be 2, then H is normal in G. So for that, first we shall consider A to be an element in G, and since index of H in G is 2, H and AH are the only left cosets of H in G, and similarly H and HA are the right cosets of the only right cosets of H in G. Now also, because they behave like equivalence clauses, the union should give rise to G with left coset as well as with the right coset, and their intersection should be null set. So we have this, and so from these two we conclude that AH is equal to HA. So by one of the criteria for H to be normal, we conclude that H is normal in G. So that can be visualized from this diagram also. We have G being written as the union of these two, and these two are disjoint, and similarly G is also being written in this way. So there is no other go. Your AH should be equal to, this must be equal to HA. Next result is every subgroup of an abelian group is normal. So we shall consider H to be a subgroup of an abelian group G, and we'll take G to be in G, and if you consider GH G inverse, because your G is normal, HG inverse can be rewritten as G inverse H. So you have as sets also they are equal whenever G is abelian. So we can have like this, where GG inverse is identity element, and identity element is present in H. So you have this to be equal to H, and that shows that your H is normal in G. Next is the center Z of G is normal in G. It is already known that Z of G, which is the collection of all elements in G which commute with all the elements of G, is a subgroup of G. So to prove the normalcy condition, we consider A in G and AZ in Z of G, and this A is at A inverse, and because Z commutes with all the elements, we can rewrite that as A inverse Z. So you have AA inverse to be identity element, and EZ is nothing but Z, and that belongs to Z of G because your Z is in Z of G. So Z of G is normal in G. Now if the question is asked in a 5 marks question, we have to prove that this Z of G is a subgroup by showing that it is non-empty, and for any two elements x and y in Z of G, x dot y inverse belongs to Z of G. That must be established, and then only normalcy condition is to be checked, as we are going to do in the next case. The intersection of two normal subgroups of a group G is normal subgroup of G. So to prove that, we shall consider N and M to be the given two normal subgroups of G. And first we note that because identity element is present in both N and M, it must be present in the intersection, and therefore the intersection is non-empty. And we consider two elements x and y in N intersection M, and because it is in the intersection, they must be there in N as well as in M, and because N and M are subgroups, x dot y inverse belongs to N as well as M, so it must be there in the intersection. That proves that N intersection M is a subgroup of G. Now to prove the normalcy condition, we have G, we shall consider G in G and X in N intersection M. Now because X is in N intersection M, it has to be there in N as well as in M. Now as N and M are normal in G, Gx G inverse should be in N as well as in M, so it must be there in the intersection. So that proves that N intersection M is normal in G. And the next video will have some of the solved problems from section 2.6. Thank you.